So thanks everybody for attending. For today, we have a speaker, Maarten Baes. He's professor at the Observatory of the University of Ghent in Belgium. Before his professorial position, he held postdoctoral jobs in Ghent, Cardiff, and as ESO fellow in La Silla. He's an expert on interstellar dust in galaxies and the radiative transfer methodology that is implemented in numerical simulations of galaxy formation to include the effects of dust. He has also worked on other aspects of galaxy evolution, dynamics, supermassive black holes, and AGN activity. Maarten is a science team member supporting a wide range of world-leading instruments. So now mentioning just MIRI at James Webb, METIS at ELT, as well as ESA missions Euclid, Athena, and Arrakis. So Professor Baes will give us a seminar within the remit of J1 on comparisons between simulated and real galaxies, with emphasis on the role of dust. As you may know, today's speaker leads the SCIRT radiative transfer project that has been implemented in the largest simulations of galaxy formation. So thanks so much, Maarten, for volunteering to give a talk, and please take it away. Thank you.
Thank you so much. All right. You should be seeing my screen now.
Yep. Haha.
Et voilà. All right. Good. So indeed, my name is Maarten Baes from Belgium, Ghent. For those who, oh, that doesn't work.
Interesting. There's a, yeah.
Ah, now it works, yeah. For those who don't know...
no, but now, Maarten, sorry. Now I have seen the background, just a Hubble Deep Field type of image.
That's it.
So I think... So
that's
okay, perfect. Sorry.
No problem. So for those who don't know Ghent, I'll show you where it is. This tiny country that you see here in red is Belgium. So it's a very tiny little thing in Europe. This is it. Most of the people know Brussels and think Belgium is actually Brussels. And Brussels is the capital of Belgium, but also the NATO headquarters and the European Union. And then Ghent is a town like 50 kilometers away in the northern part of the country. It's actually quite beautiful. It's an old town, so full of medieval buildings. So if you ever in the neighborhood, contact me and we're happy to arrange a visit for you. Good. So what we are doing with our team in Belgium, in Ghent, is look at galaxy formation and evolution, different aspects together with my colleagues. And the grand questions there, of course, is where do these galaxies come from? How do they evolve? And why do we see the different types of galaxies that we observe in the universe, both today and at higher redshift? And if you see, there are many, many different types of galaxies, not a real image. It's a collection of all things put together. But there are different shapes, different colors. And so we want to find out how do these form throughout the history of the universe. There's different ways how this can be done. And in the past, I would say maybe decade or 2 decades, one of the methods that has increased in importance is cosmological galaxy formation simulations. So numerical simulations that attempt to simulate the formation and evolution of galaxies. And by putting in massive computer programs, the recipes, the physical recipes that we think are important in the evolution of galaxies, like gravity, gas cooling, heating, star formation, stellar evolution, and so on, try to then simulate a whole slice of the universe over cosmic time. And there have been quite a number of these simulations in the past few years, and they can roughly be subdivided in 2 regimes. Either you have like what we call the large volume simulations that are typically big volumes, roughly something like 100 megaparsec cubed, which then contain thousands of galaxies, and where you can then at the same time simulate the evolution of the entire galaxy population. Those are the ones that you see here on the left. On the right, you see a different regime. Those are zoom simulations, where we zoom into the formation of a single or a few galaxies, with then the advantage, of course, that you have much higher resolution, but you have not a view on the entire galaxy population. And you can see that more schematically or more more clearly here, where you see on the left-hand side, you see the resolution of the simulations in co-moving parsec versus the box size. And the large volume simulations, they have indeed these typical volumes of 100 megaparsec cubes, but the resolution is then quite poor, with typically around kiloparsec resolution or slightly better. And then the zooms are much smaller volumes, but of course higher resolution. And if you look at on the right-hand plot, you have the same thing on the x-axis, so the box size, the slice of the volume that you look at, and then you have here you have the mass resolution. And so if we look at these big simulations, we're talking about resolutions of 10 to the 6th, 10 to the 5th in baryons, whereas for the zoom simulations, we can have 1 or 2 orders of magnitude better resolution. But of course, so both of them have their advantages and their disadvantages. So there's a lot of these simulations. I'm just showing a movie from one of them. This is from the TNG simulation. I'm not involved in this. I'm just stealing their videos, and it's really beautiful, the level of detail that you can get in these simulations. So what we're seeing here is the gas in forming in a single galaxy taken from that simulation. And in the zooms, you have here like the wider region. This is the stellar mass image. This is again the gas, and this can go on and go on. So it's really fantastic what these galaxies can do these days. However, if you run such a simulation, which typically takes for months on a supercomputer, they only are meaningful, of course, if the galaxies that come out of these simulations are kind of representative for the galaxies we see in the universe. So it's not very useful to run simulations that come out, and the galaxies that come out of them don't look like the ones we see around us. So it is crucial to compare the simulated and observed galaxies so that we can, for example, calibrate the physical processes that go into these simulations, or that we can also then make somewhat realistic or meaningful predictions for the galaxy population. And there is an issue, because it's not the same thing what we see from the simulations and from the galaxies we observe. If we look at numerical simulations, what we get is essentially a whole list of particles or cells. We have stellar particles. Each of these particles has many, many properties, like their position, their velocity, metallicity, all kinds of things. Same with the gas particles. And from these particles, we can calculate physical galaxy properties like the stellar mass, the star formation rate, all of these physical quantities we can easily calculate for these simulated galaxies. On the other hand, if you look at galaxies either nearby or in the distance, what we measure is the light distribution on the plane of the sky. And this can be the 2D light distribution, can also measure kinematics or polarization or other things, or spectroscopy. So in the end, we get fluxes, images, SEDs, polarization maps, all the typical observational diagnostics that we can measure. And this, of course, is not the same. We can talk, these are apples and the other is oranges, and we cannot immediately compare the apples and the oranges. If we want to compare them, we either have to turn the oranges into apples or turn the apples into oranges. In other words, we have to compare simulated and observed galaxies either in the physical domain or in the observational domain, right? And both of them are often done, and both of them have their advantages and disadvantages. And comparing them in the physical domain is what we typically call inverse modeling. That means we compare simulated and observed galaxies in terms of the intrinsic physical galaxy properties. Think about the stellar mass, the star formation rate, the star formation history, and all of these physical properties. For the simulated galaxies that come out of the galaxy formation simulations, these are readily available. If you want to measure the stellar mass, you just look at the stellar particles and add their masses. So that's very simple. For observed galaxies, then it is a bit harder, because you you need then to derive or to infer the physical properties from observational data. And this can be done with different levels of sophistication or complexity. And the simplest thing is to use recipes to convert observables into physical properties. Think about you have a luminosity and a color, and then you calculate your stellar mass from those data, or you calculate or you estimate the star formation rate from, let's say, the UV flux or from the infrared flux or a combination of those two. So there's a lot of recipes that are being used. You can also use more complex approaches, machine learning, and so on. But it's not a surprise that in this community, people will be very happy with you looking at SED fitting. And that is a very popular practice and probably the most reliable way to get physical properties out of observed data. And you see here an example, a somewhat old example from Groves et al., where you see a lot of broadband data as a function of wavelengths. You fit a certain SED model through it, and from the model that fits best, you derive physical properties like here, the star formation rate, and so on. Now, this is a field that has, and this is the topic of this entire commission, so people attending here might know much more about that than I do, but this is a field that has been advancing a lot in the past decade, I would also say. And this is some examples of more advanced results. So this is work from Angelos Nersessian, who's a postdoc in our team, where he fits a combination of photometry and spectroscopy at the same time with a full Bayesian inference of then the parameters. You get your estimates of your best fitting parameters, but also the entire posterior distributions. You get the star formation history and so on. So this is already quite advanced. This is work from Abdurrauf, who's also here attending, where he fits not entire galaxies, but fits individual pixels. So you can look at an individual pixel or a region in a galaxy, get the SED of this entire region, and then again fit the best fitting model through these data points, and then get not global parameters of the galaxy as a whole, but parameter maps. So all of this has come to a certain level of maturity, but there are still some challenges involved in inverse modeling. And essentially, this SED fitting or other types of inverse modeling always come with strong, or I would say even simplistic assumptions. Not everybody's using simplistic things, but there's always some assumptions, even if they are implicit, that you make. For example, you have to assume a certain star formation history. I would say 20 years ago, people just used a single SSP with a single age. Now this is much more broad, but still, if you look at what comes out, for example, from a numerical simulation, this is the pink line here. This is the star formation history of a simulated galaxy. You can never kind of reproduce that exactly with an analytical function or even with a non-parametric star formation history. So there's always assumptions that you make. Same accounts for the chemical enrichment history. We know that in galaxies, different stars have different metallicities. If we do SED fitting, it's often assumed that we have a single metallicity. Not all codes do that, but there is assumptions that one has to make. Same about the star dust geometry, about the dust emission spectrum, where people often use like a single temperature black body, things like that. These assumptions are very hard to avoid. And apart from that, another challenge is that some interesting aspects of galaxies are hard to compare in the physical domain. If you look, for example, at galaxy morphology, which includes a lot of information, it's very hard to convert that to a physical, in the physical domain. Same with polarization and so on. So an alternative way of comparing simulated and observed galaxies is what we call forward modeling. And so then we are in the Apple domain. This is in principle more flexible because you can account for, in principle, any star geometry. This can be fully 3D. There's no limitation on that. You can include any star formation history, any metallicity distribution. And in that sense, there are fewer assumptions that one has to make. I'm not saying there's no assumptions. You always make assumptions, implicit or explicit. But in this aspect, I think the forward modeling is potentially less biased. And you can also then do an apple-to comparison with other observational aspects, for example, morphology, polarization, velocity structure, and so on, that you can then simulate and compare directly in the observed space. But of course, if you want to compare cosmological simulations or simulated galaxies to observations, this requires the production of mock observations. And of course, they have to be as realistic as possible. And this is what many people nowadays also do. And in principle, one might think it's not so difficult. It's relatively easy. Imagine that you have a simulated galaxy. This simulated galaxy consists, if you look at what comes out of your computer, consists of a list of a few million, say, star particles. Each of these star particles has a mass, metallicity, and age, and so on. So what if you want to make a mock image for such a galaxy, what you do is you take this list of all your particles. Every particle you assign an intrinsic spectral energy distribution from, say, an SSP library. Then you project each particle on the plane of the sky. Your plane of the sky, you subdivide it into pixels, and you add in every pixel the contribution of all particles. And what you end up with is just a projected image. And this is like, for example, from the Illustris simulation, these are such images created in this way. And in the same way, you can make color maps, line strength maps, velocity maps, and so on. In principle, that is not so difficult. But of course, there are trouble. And one of the troubles along the road is interstellar dust. These are just tiny solid particles. We're talking about submicron sized particles. The ones you see here are not interstellar dust grains. These are interplanetary dust grains, are much larger, but of course we don't have interstellar dust grains pictures. They are created in stellar winds, in supernova explosions. They grow, they evolve in the interstellar medium, and we believe this. You can talk about that for a whole other seminar. What we think these grains are made of, and we think that largely there's two different types. We have silicate grains and carbonaceous grains. Some of them can have mantles, can have iron cores, and so on. But always think about silicate grains and carbonaceous grains. And silicate grains are just small sand grains. Carbonaceous dust grains, they're just smoke or root. So the space between stars in a galaxy contains fractions of sand and root. And soot, sorry. But does it matter? Should we care about interstellar dust? And naively, one would say no. Because if we look at the mass contribution of interstellar dust, and there's ways to estimate that from observed data, for example, using SED fitting. If you look at nearby galaxies, this is both work from the Speedia galaxy sample. On the left, you see the dust to stellar mass ratio as a function of stellar mass. And you see that typically the amount of dust is less than 1% or even less than 0.1% of the total mass in stars. So that's really negligible. On the right, this is the dust to baryon ratio, and then of course it's even lower. So there is not that much dust in galaxies. The canonical value of the gas to dust ratio in the Milky Way is somewhere between 100 and 200. That's gas to dust between 100 and 200. So it's, in terms of its mass contribution, it's really negligible. But it is important, and that is because dust grains interact quite substantially with radiation, with starlight. And there's several ways of interaction, and one of the effects that is very efficient at especially UV and also blue wavelengths, and in the optical as well, is dust absorption, and that you see here clearly illustrated, where you have a molecular cloud core in front of a background field of stars, and there's no stars visible here because the dust in this molecular cloud core just absorbs all the starlight. And so this just blocks an entire fraction of the starlight that would otherwise reach us. There's also scattering. That means that when photons interact with the small dust grains, their energy is not converted into thermal radiation, into heat, but is just reflected and propagates in another direction. And that's why you see around in star-forming regions, you have these scattering halos, also because UV and blue light scatters very efficiently. And then you have thermal dust emission, because if dust grains absorb starlight, meaning if they convert the energy of starlight into internal energy, this energy is then re-emitted thermally in the infrared. And then we see that from mid-infrared all the way to millimeter wavelengths. There's other processes that happen, but these are important for this talk. And if we look what this does on galaxy scales, this is a well-known, a typical view of an SED going all the way from UV to millimeter wavelengths. And what we would see if there were no dust in a galaxy would be the blue line. This is like the combined SED of all the stars in this galaxy. But what we do observe is then the reddish line. Of course, we observe the black points, and the red line is a fit through these data. And we see that in the UV optical, a part of the starlight is attenuated by dust. And if we look in the infrared, so mid-infrared to submillimeter, the emission is completely dominated by thermal dust emission. So it does play a role in how galaxies look. And if we look at this statistically and we ask ourselves the question, so how much of this starlight is being attenuated and converted into infrared emission? This is work from more than 20 years old in the time of ISO mission. And you see that roughly 1/3 of the entire emission of galaxies is emitted in the far infrared, meaning 1/3 of all the starlight is absorbed and re-emitted as thermal emission. And the same result actually remains if we go to later missions. This is based on Herschel. Again, roughly 1/3 of all the starlight is attenuated. This is still later, roughly 1/3 is attenuated. So should we care about interstellar dust? Now the answer is yes, because it absorbs 30 to 50% of all the starlight in galaxies and converts it into thermal infrared emission. So predicting galaxy spectra, SEDs, images without taking into account dust attenuation and dust emission can give you very wrong results. So let's do that. And this is an example where this practice is really shown in much detail. This is Andromeda, where you see here the very dark dust lanes. So this is where starlight is being absorbed. Same here, all these dark lanes. If we look at the same galaxy, but now in the far infrared, and this is what we could do thanks to Herschel, you see that exactly there where there was dust absorption, now the galaxy shines bright in far infrared emission. So you see here really the conversion of absorption into thermal emission at work. Right. And that's a combined image. Okay, so if we want to take these effects into account, we have to do dust radiative transfer. Now hold your seats, we're going to do mathematics. Well, just one equation in this entire talk. If you want to calculate the effects of dust on the radiation in galaxies, we have to solve the dust radiative transfer equation. And I'll walk you through this equation, very simple, or in a very simple way. The quantity that we want to solve is the intensity of light. Think of it as the number of photons. Now that is the number of photons of the intensity at a certain position, x, propagating in a certain direction, and of a certain wavelength. So this is 6 dimensions. Can also depend on time, but let's ignore time dependence for the moment. So what we want to know is how this intensity changes if the radiation goes along a certain small distance s. Now, how is this radiation field affected? Well, there's different aspects that cause this change. And one of them is just, well, photons can be added because they are emitted by stars there. This is what we call the stellar emissivity. So radiation field can become stronger because stars add photons to it. It can also decrease because of absorption and scattering. If dust grains are in the way, they can absorb the light or they can scatter it into the other direction, and you get another term with a negative. Then there's also scattering into the line of sight. Now it becomes very complicated, don't worry about that. And there's also thermal emission by dust grains. You have these different physical mechanisms that are at play here. Okay. The only thing I wanted to show here that this is a terrible equation to solve. It is a difficult equation because it's a partial integral differential equation in 6 dimensions. It's non-local in all dimensions. You can have scattering where it just changes wavelength. It can be absorbed and re-emitted in another wavelength. And then you have this term here, which looks very simple, but this actually depends on the intensity in a very complex way. So this is a horrible equation to solve. And so some people like myself have devoted their life in trying to solve this equation. And other people say, but why don't we just simplify it? Can we not simplify this radiative transfer problem? And that is, of course, very interesting because that saves you a lot of computational work. You can, for example, just plainly ignore the dust. You can approximate scattering. You can neglect scattering. You can use a simple screen geometry, an absorbing screen. All of these things make life much more interesting, much more simple. But since the late 1980s, when computers were strong enough to actually solve these equations properly, many authors have been stressing that these simplifications are never satisfactory. And we still keep doing that because people, of course, are still attracted by doing this in a simple way. And I would say one of the godfathers of radiative transfer was Adolf Witt, or is still Adolf Witt. And I really like what he wrote in his 1992 paper saying, much previous work on the effects of dust on stellar radiation has been simplistic, wrong, and usually both. And I'm happy to say that nowadays more and more people are actually doing radiative transfer properly, and I would like to encourage people to keep doing that. And so one way to help encourage people to do radiative transfer properly is to make codes that do that for you and to make them publicly available. And this is what we've been doing in our group in Ghent for more than 20 years now. And we have developed the SCIRT code, which we are still continuously developing with a very nice team of people, and that we are using for many different kind of radiative transfer problems. And in the context of what I'm telling about today, this is currently one of the applications that we're using it most for. That is radiative transfer post-processing of simulated galaxies. And again, in principle, the idea is not so complicated. So what we do is we take out of a simulation, we pick one galaxy, and we want to generate, say, images for this galaxy. So what we do is we take this galaxy, we look at all of the particles or cells in this galaxy. Then we do some ordering depending on the age. The stars go into different categories. The gas is transformed into dust. So we have dust and star particles, let's say it. We then put these on a radiative transfer grid such that we can perform the radiative transfer. We position some instruments, some fake instruments. Then we run the radiative transfer and we generate images for these galaxies. But there are some tricky parts into this, what we say, pipeline, and I'll go over a few of these tricky aspects, but many of these things are described in several papers here. And for example, assigning a spectrum to the stars is not so simple. Positioning the dust in the galaxies is not simple. Setting up a grid is not so simple. Doing the actual radiative transfer is not so simple. So we have to think about all these things in some detail. And I'll go over these 4 aspects. So if we want to assign, say, a spectrum to a star, in principle, that is easy because from the simulation, every star particle, we know its stellar mass or its initial stellar mass, we know its age, we know its metallicity. So we can, in principle, just assign a template SED from an SSP library, and there are many SSP libraries available. I know many of you work on this, so I assume that it's not something new I tell you. So that is, in principle, not so difficult. But one issue is that young stellar particles are still in birth clouds. And we're looking at young particles, we're talking about up to a few million years old. They are still embedded in their birth clouds, and these birth clouds are unresolved by the hydrodynamical simulation, meaning we have to put the dust around it artificially ourselves. And so for those young stars, we have to use special template libraries that take into account the circumstellar or circumstarburst-like attenuation and emission. And there's different of such libraries available. And one of our postdoc students at that time, postdocs at this moment, developed such a library called Toddlers, where he looks at the time evolution of such a star forming region within a dusty envelope, then calculates the dynamical properties of this circumstellar material, and then calculates the resulting spectra. And these are then used as templates for these young stellar particles in our simulation. Another aspect that is far from trivial is inserting the dust in the simulations, because these cosmological simulations, and especially the ones with large volumes, they do not include dust as a species in their hydrodynamics, meaning what comes out of the hydrodynamical simulations, the galaxy formation simulations, is lists of particles or cells with the gas properties and so on, but dust is not involved. Also because dust is such, dynamically spoken, such a minor component. So if we want to do radiative transfer, we have to manually put the dust in the simulation. But yeah, how do you do that? Well, the way this is typically done is we use a recipe or a proxy for the dust in the simulated galaxies based on the properties of the ISM. And the most common approach is to use a fixed dust to metal ratio. So we assume that a constant fraction of the metals in the gas are locked up into dust grains. Now this gives us a free parameter in the post-processing, And then we try to calibrate this free parameter by comparing it to observations. And this is, for example, work by Anna Trichka, where she ran a lot of simulations with different values of this F dust, this dust to metal ratio parameter, compared it to a set of galaxies, and then looked which value reproduced the data best. Now she still is a very careful student and spent months on trying to calibrate this process. So it's a very painstaking process. Now, some recent cosmological simulations, we don't have to do that anymore because they do include dust physics. I'll come back to that later in this talk. Now, a third aspect that needs a little bit of attention is that the medium, so the dusty medium through which the photons fly in our simulation, must be discretized. So it has to be discretized onto a grid, because otherwise you cannot do the radiative transfer. Now, setting up such a grid is relatively simple if you have very idealized simulations. But if you're looking at these cosmological simulations where everything is very 3D and non-structured, you have to think about which grid is most fit for the purpose. And the ideal specifications of such a grid is that it contains as few cells as possible, because the runtime of your radiative transfer simulation essentially scales with the number of cells. The more cells, the harder it is. But still, you want a large dynamic range, and you want to resolve the regions that need to be resolved. So these two are a little bit opposite requirements to each other. And on top of that, you want a kind of grid where propagating photons, so your photons go from one cell to the other, that should be as efficient as possible. And several radiative transfer teams and our team as well have done quite some research in finding out the best or exploring different grid types and the associated ray tracing algorithms through these grids. And we can work with hierarchical grids, so think about octree grids, where you can refine your grids at the locations where it is needed. Or we can use Voronoi grids, and this is quite interesting because some of the hydrodynamical simulations are also run on Voronoi grids, so you can couple it immediately to the hydro simulation. Or we've also explored tetrahedral grids, which was not a major success, but in any way, there's been a lot of research gone into finding the optimal combination of gridding and ray tracing through these grids to make the radiative transfer simulations as efficient as possible. And the last aspect that I want to focus a bit on is the calculation of the thermal dust emission, because this again seems relatively straightforward in principle, because if we know where radiation goes, the starlight, and we can then in principle in every cell of our simulation volume, we can calculate the interstellar radiation field. So we can essentially count how many photons of each wavelength pass through this cell every second, right? Now, if you know that, then you can calculate the dust temperature distribution in that cell. And if you know the dust temperature distribution, then you can calculate the thermal emission over the entire infrared wavelength regime. And this is not simple because you have these non-equilibrium dust emission and so on. And so this by itself, this is already like a complicated calculation, but one should not forget that this has to be done for every grid cell, and we're typically talking about millions of grid cells, for every grain type, because silicate and say carbonaceous grains get different dust distributions, and for every grain size bin, because small and large grains get different distributions. So this has to be repeated many, many times, and sometimes iteration is required because you can have dust self-absorption. the emission by the dust can be absorbed again, which leads to iteration. So this requires some computing power. But in the end, this is all we've spent we and other teams spend a lot of time in optimizing all of these processes, and we can now post-process these cosmological simulations. And in the work that we've been doing in the past few years, we've focused mainly on 2 simulations, some others as well, but most of our focus has gone to Eagle, which was one of the big simulations now 10 years ago. And it has had several runs, but the runs that we focused on were one with 100 megaparsec on the side, and then like a zoom or smaller, higher resolution 25 megaparsec volume. And we looked at IllustrisTNG, which is a bit more recent, talking about 19. Again, it comes in 300, 150. We didn't look at TNG 300 because the resolution is a bit coarse for what we're doing, but we looked at TNG 50 and TNG 100. So each of these simulations, if you look at redshift 0, contains more than 5,000 galaxies at redshift 0. So it's significantly big to do like a real analysis of the entire galaxy population. And so the simplest thing you can do is to look at integrated broadband fluxes and SEDs. So essentially, you take a galaxy, you do the rate of transfer calculation, and you calculate the flux at every wavelength. This has been done for 10,000s of galaxies of different simulations. Why? Because this is actually relatively cheap. Because to get the full flux, you don't need that many photon packets. So typically for a galaxy, this can be done in less than an hour, or typically much less than an hour. So it's relatively cheap. And so here you see 3 SEDs. This one, the bottom one, is an observed galaxy. The other ones are simulated galaxies from the Eagle simulation. This is from the higher resolution Eagle simulation. This is from the reference Eagle simulation. And you see these look pretty the same or pretty comparable, meaning that what comes out of our rate of transfer modeling looks reasonable at first sight. But of course, we want to do better than just look at them by eye and compare the properties of the simulated galaxies to the actual observed galaxy population. And for example, what we see here is a comparison of the star formation rate in Eagle galaxies. This is the actual star formation rate from the simulation. And what you see in the different panels is the estimated star formation rate from typical observational traces. For example, this is from the NUV band, this is from the total infrared, this is from the 24 micron band. And you see that on average, there's reasonable agreement between the actual star formation rate and the one that you derive from simulations, but there are a number of differences. And for example, here you see if you look at the total infrared emission as a star formation tracer, you sometimes overestimate this star formation quite dramatically. And this is because dust is not only heated by young stellar populations, but especially in the regime of low star formation rates, it's also the old stellar populations that can contribute to the dust heating and therefore to the total far infrared emission. This is work by James Treyford, who looked at the stellar mass versus optical color diagram. This is again Eagle work. And so what you see in the colors is the results from the Eagle simulation, and in the contours is observed galaxies from Gamma. And we all know that in this diagram, stellar mass versus color, you should see 2 populations. You should see the blue cloud, which is here, and you see the red sequence of galaxies that are hardly star forming. Now, if you look at the correspondence with the Eagle results, you see that the correspondence is not very good. The red sequence should be here, but you see it here and here, so it's not very good. But this is without radiative transfer. If you apply radiative transfer with skirt, then you get this result where now the blue cloud is where it should be, and indeed you start seeing a clear red sequence here. So the effect of dust are really important if you want to get this right. This is a plot. This is the cosmic spectral energy distribution. So this was work we did after we radiative transfer post-processed all the galaxies. We thought, what if we add all of these galaxies together? Then we should have the total emission of the universe, of say cosmic volume of universe. So this is the total power as a function of wavelength per unit volume in the universe. And what you see here in gray squares are measurements from the gamma survey, and the green points are just the Eagle skirt results. And we see that this looks pretty okay. So this did not include any fine-tuning at all after, of course, the initial calibration that we applied in the beginning. So we were pretty happy about that. Although there are a number of aspects where this does not agree very well. And especially we look at the UV, we see that we don't have enough attenuation at UV wavelengths. And we think this is because of our treatment of the young stellar particles. We don't have the templates that we used at that moment were not good enough. And that's why we developed these toddlers models where we think this would now be better. We can also look at luminosity functions. So these are luminosity functions at redshift 0 now of the TNG, IllustrisTNG simulation. So in the symbols are observed data, and the lines are the results from cosmological simulations, where you see the purple is TNG 50 and the green is TNG 100. And you see that in all of these panels, this is UV up to optical, you see that the purple line overestimates the observations, meaning there is too much emission in the TNG 50 simulation, essentially at all wavelengths. And you have, if you look at the TNG 100 simulation, there we see an excellent agreement with the observations, given that, of course, also in the observations, there is sometimes a little bit of discrepancy. But we can say that TNG 100 does a very good job. TNG 50 overestimates the luminosity functions. And we see the same if we go to longer wavelengths. So this is then the near infrared, and here we have Herschel and the total infrared. See, the red goes through the data almost everywhere, the purple does not. The reason for that, so we wanted, of course, to find out why that was. And the reason for this discrepancy is that the subgrid parameters in the TNG 100 simulations are calibrated at the TNG 100 resolution. And so the TNG 50 resolution, which is higher resolution, assumed the same parameters, but this resulted in too much star formation and too much mass. So we know that on average for a given dark matter halo mass, the TNG 50 galaxies are typically up to 50% too massive. So this explains this discrepancy. A last aspect that we looked at when looking at global fluxes was colors. And if we look at colors at redshift 0, so the local universe, there we see we looked at many different colors. This is work by Andrea Gebeck, who just last week defended his PhD thesis in our institute. And so if you look, for example, this is R minus J versus U minus R. This is FUV minus K versus K minus spire 250, but you can take any possible combination. At redshift 0, this agrees pretty well with the observations. So the red contours are TNG 100 results. The gray contours are observed galaxies from the gamma survey. And you see here, this looks pretty good. Okay. At redshift 0, essentially we find that our radiative transfer post-processing agrees very well with the observed colors. Now, if you look at cosmic noon at redshift 2, there the story is quite different. So what we see here is the so-called UVJ diagram. This is an often used color diagram to separate star forming from quiescent galaxies. So typically we have the star forming galaxies in this part of this color diagram, and the quiescent ones are in this corner here. This is what you see. If you look, for example, this is the specific star formation rate. The ones with the lowest specific star formation rates are located in this part of the diagram. Now, in this plot, Andrea looked at the UVJ diagram at redshift of about 2. That's a lot of James Webb observed a lot of galaxies here. And the galaxies are here split in different bins in stellar mass. So these are low mass galaxies, these are high mass galaxies. And if you look at the observed galaxies, that are the gray contours, then we see that at low masses, this agrees pretty well with where the galaxies in TNG are lying. But if we look at massive galaxies, you see there's a lot of galaxies here in this part of the UVJ diagram, where the simulated galaxies are here. Now, these are results without dust attenuation. So you think if we put dust into the simulations, galaxies will shift in this direction because they will be reddened. And so we did that, and this is the result. If you look at the low mass galaxies, this is still somewhat acceptable. But if you look at high mass galaxies, we can just not explain these very red colors. And we tried, or Andrea tried, by putting more dust in it. Like putting all of the dust in, all the metals into dust, you can never get these very red colors. And so with the setup that we have, it is just impossible to explain the red colors of massive galaxies. We also tried with different SSP libraries, it didn't work. The only thing that we found that could work is that if you put dust screens around the younger stars, about all the stars younger than 1 gigayears, if you redden these in specifically, then you might get these very red colors. But this is not that we get if we use our standard recipes. So this tells us that at high redshift, the standard fixed dust to metal ratio is probably not going to work out. And so this is work to be looked at in more detail. Now, apart from these global fluxes and colors and SEDs, we can also look at data on sub-kiloparsec scale, because that is then a more powerful test for galaxy evolution models. Looking at, instead of single fluxes, you get complete images or data cubes. And then you can probe different things like morphology. You can look at sub-kiloparsec scaling relations, where you look at, for example, color versus dust to mass ratio. These are all pixels in Andromeda, so you get these certain relations. You can look at kinematics and so on. Of course, this is computationally much more demanding because you need to shoot a lot more photons before you get a very nice converged image. So you need bigger or more computers. And this was one of the first mock images that we made. This is from the ERIS simulation, where you see that now we have a very detailed image with, if you look at edge on, you see a nice dust lane appearing, and we now go through the galaxy. But this takes a lot more computation time. And we can not only look how this galaxy would look like, say, in optical light. So this is like an RBG image in optical light. We can also look what this galaxy would look like in the far infrared, like in dust emission. We make predictions of how this would look. And the same at all different wavelengths. One of the first efforts where we did this high resolution post-processing was for the set of Auriga galaxies. It's another cosmological simulation, but now a zoom simulation, so with much higher resolution. Fairly recently, we released what we call the TNG50 Skirt Atlas. So that's a multi-wavelength atlas of images of more than 1,000 galaxies at redshift 0 from the TNG50 simulation, and where for every galaxy we generated images in many different, more than 20 different bands from different inclinations. And we're now expanding this atlas to also include dust emission maps. If you want to look at these images, it's a lot of data, but they're all publicly available on the TNG data archive. So we invite you to play with them. And of course, we also looked at a number of diagnostics that we could derive from these images. And what you see here is the relation between absolute magnitude, effective radius, and wavelength. So the purple data here are observed data from the Siena Galaxy Atlas. The gray data are data from the TNG50 simulation. And what you see here, this is for the reddest population. We see that we reproduce fairly well the radius, the relation between effective radius and absolute magnitude, meaning the more massive galaxies are on average larger than the less massive, less luminous galaxies. But what you also see here in this plot is the different symbols correspond to different wavelengths, different bands in which this effective radius is measured. And both for the observed galaxies and for the simulated galaxies, we see that the G-band effective radii are typically larger than the Z-band, meaning that galaxies appear smaller in longer wavelengths. And you see that essentially for in every mass bin and in every color bin. So here the correspondence between observations and simulation is a bit less good. But if we focus on that aspect, we can calculate the dependence of effective radius as a function of wavelength. And this indeed, we see that galaxies appear much larger in blue light and they appear more compact in redder light. And there's two different effects that can cause this wavelength dependence. It can be stellar populations that, and we know that like blue stars, younger stars are typically more spread out in the disk, whereas older stars are typically in the bulge. So you naturally get a color gradient, which translates into this relation. On the other hand, you also have dust attenuation, because dust is more effective at blue light. And since there is more dust in the center, more light from the central regions are absorbed in the blue wavelengths, meaning this also causes the galaxies to appear more extended at shorter wavelengths. And because, of course, we have for these galaxies both the dust attenuated and the images without dust attenuation, we can separate these two effects. And what we found is that stellar population gradients are responsible for 80% of this trend and dust attenuation only for 20%. We also looked at the non-parametric morphology of TNG galaxies and studied the wavelength dependence of the morphology. This is work by a student. His first paper is about to be submitted, where he looked at standard non-parametric indicators such as concentration, asymmetry, smoothness, Gini M20, and the bulge statistic. And we see that these measurements do depend on wavelength. And so the red lines are bulge-dominated galaxies. Blue is the disk population. And the yellow line here are the average results from the SINGS galaxy sample. And we see that actually our results agree fairly well with observed relations, which is actually not so trivial, because the cosmological simulations can never be fine-tuned based on morphology. That is something not you can calibrate. So the fact that this comes out of the simulations is actually quite reassuring. Now, as I told already, one of the major challenges that we have in this post-processing methodology is that these simulations do not contain dust. More actually, they usually do not contain a cold ISM, which means that we have to insert the dust ourselves, and this comes with quite some uncertainty. Now, a new generation of simulations is now being run, or some results have already been available, which do include the physics of the cold ISM, now with cooling down to 10K, so meaning we will really have a multi-phase ISM, and with explicit dust physics, meaning they model the creation, destruction, and evolution of dust grains throughout the simulation. And the effect of these things are actually quite substantial. So if you look, this is the phase diagram of gas in the TNG 300 simulation. So this is of all the gas cells in the entire volume. We look at the density versus the temperature, and we see here like the phase, and there's essentially no gas cooler than 10,000 K. So this gas, which should normally cool, is artificially kept at this temperature level, and then the star formation recipes are a subgrid recipe. Now, if we look at new simulations, this is from the COLIBRE simulation in the same, so this is the same axis. So if you look here, the old simulation, this is the new simulation, we see that gas now can cool all the way to 10K, and you get a much, much wider variance in gas properties. Now, this simulation also contains dust physics, so we can also look at the dust to metal ratio, which in our previous post-processing always kept constant. Now, if the color scale here is the dust to metal ratio, you see that this is very different throughout this phase diagram. So it could be possible that much of the work we've been doing can be improved by taking into account more realistic distributions of the dust. And this is not simple, of course, to include this dust physics. There's a lot of mechanisms that need to be taken into account. This is from Frederic Galliano, very beautiful diagram with all the different things that can affect dust physics. So you have grain growth, you have astration, you have fresh star dust, but you have photodisorption, sublimate. There's all kind of things that is happening, and taking that into account is a really impressive achievement. One of the simulations where this has been done is the new cluster simulation. This is a simulation that is still running at this moment, but some galaxies up down to redshift 1 have already been analyzed. And this is work that's been recently published by Baes et al., where they see that the dust to metal ratio in these massive high redshift galaxies is not constant. And so we looked at how would the galaxy look like if we use the on-the-fly dust distribution. And this is how this galaxy would look like if we use dust attenuation where the dust as it is formed. And this is what the galaxy would look like if you use a fixed dust to metal ratio. Now on the screen, you don't see it that differently, but the results are quite different. And for example, if you then look based on these two different recipes for putting dust in your galaxy, and you look at, for example, the fraction of late type galaxies as a function of redshift, where this is whether a galaxy is late type or not is determined by the optical morphology, you see that there is quite a difference. So if you look at galaxies, the red line, where you look at on-the-fly dust, this is what you get here, the red line. The blue line is what you get if you use a fixed dust to metal ratio. And you see you would get much more late-type galaxies, whereas if you use the red line, you are closer to what we see in JWST Cosmos observations. And now the big next step that we are working on now as well with our team in Ghent is the COLIBRE project. So this is the follow-up of the Eagle set of simulation, but yeah, better in all aspects. And the main aspect in which, the main aspects in which it differs from Eagle, apart from essentially everything being improved, is that it covers larger volumes up to 400 megaparsecs, but also includes a cold ISM and a live dust model in the simulation. And so this for us is quite interesting because it takes away some of the uncertainty that we have in our post-processing. And this is a first result from COLIBRE, where we just looked at one of the COLIBRE volumes and looked at the cosmic spectral energy distribution. Again, we took all of the galaxies, calculated their SED, and added them all up. And we just reproduce the observed CSED with almost no free parameters at all. So there is no dust to matter ratio that we have to fine tune. No, this just comes out of the data as they are. There are a few free parameters, but they are less important than the ones we had at the time when we looked at Eagle. So this is really, I was very happy when I first saw this graph. This is also work, again, this is very premature and in progress. This is looking at the color magnitude diagram. So we have here R band absolute magnitude. Okay, so we look here at absolute magnitude versus NUV minus R color. And so on the right-hand diagram, we have observed data in the local universe from the Gamma survey. Now, if we look at galaxies from COLIBRE, all post-processed with SKIRT, and we look at all galaxies and we plot them in this diagram, this is not really similar. We have kind of a blue cloud, we have a red sequence, but it's not at all the population that we have here. Now, this is the dust-free, so if we don't take dust into account. But of course, you can imagine dust does affect optical colors, does affect R band magnitude. So if we put dust into this picture, then we get this. Of course, we have reddening, meaning that the galaxies all move up here. So our blue clouds becomes, if you go back, rather than a sequence, really becomes a cloud and is slightly redder, which is very much in agreement with this. But we still have this red sequence here in this diagram. But this is for the entire sample. If we now also include the same observational constraints, so we have a gamma matched sample of galaxies with the same observation limits, then this red sequence almost completely disappears. And now we tend to agree much better. Much more is hopefully coming soon. We're working hard on this. And this is also what I want to end with. And so before finishing, I just want to thank all of the PhD students and postdocs in our team, and also the many collaborators around the world that have helped doing this work. So thank you for listening.
Thanks so much. Thank you, Maarten. This was a really nice talk, very pedagogical introduction. I really liked it a lot, and very interesting results. Thank you. We have time for a couple of questions. So if you want to ask a question, I mean, raise your hand, and perhaps you can just directly just switch on your mic and your camera and ask ahead. Yeah.
Hi, Maarten. Thank you very much for very nice talk.
Thank you.
Is it possible to simulate a mock IFU data cube with SKIRT? If so, how are the nebular emission line simulated in the code? And did you include like the effect of gas kinematics in the nebular emission simulations, which could broaden the emission lines? Thank you.
Yes, that is possible. There have been There have been people who created IFU mock data with SCIRT. Concerning the old stars and the young stars with their nebular emission, that is automatically done because these young stars in the libraries that we have, they do contain nebular emission around them. But of course, the diffuse gas, that is a bit more difficult. Now we are currently working on a new library that calculates the emission lines and also the nebular continuum of diffuse gas, both using photoionization and collision ionization. So these should be ready, or they are ready. They are being tested at the moment, so they should be incorporated in the public version of the code soon. And then it is definitely possible to calculate IFU cubes. SCIRT also takes into account kinematics. So if your sources have a certain 3D velocity, that is accounted for. So we can calculate Doppler shifts and then dispersion maps, line of sight velocity maps. We also had a PhD student who graduated on this topic 2 years ago. So we can make full kinematic data cubes, both in starlight and in nebular and in emission line kinematics.
Thank you.
You're welcome.
Other questions? So in the meantime, I was wondering, Maarten, one question I have is in terms of the inverse modeling. So basically, when you're trying to extract from spectroscopy and photometry, you're trying to extract some models. You were referring to, for instance, the modeling of birth clouds and the dust attenuation there. And you know that in this field, we tend to use quite a lot oversimplistic models. And one of those that is used quite a lot is a shallow unfold, where you simply say, look, you have a dust screen, but then when you have a population younger than a given threshold, then you're imposing. So what's your view on that, whether this can be improved or whether this is okay for the type of results that we're getting?
Yeah, well, the Toddler's models are essentially based on that principle as well. So, but it's not just we don't use a single parameter, but it's kind of more based on a dynamical evolution of a star or a cloud of stars forming into an homogeneous sphere, and then it pushes the gas away. You have gravity and you have stellar pressure, and these two keeping each other in balance. So it's a little bit based on the same principle. These models are still spherically metric because it's just very hard to do differently.
Yep.
And in that sense, we are aware that this is a limitation. But I think it was already a step forward in the right direction. But in principle, I'm not against using simple models if they encompass the basic physics. So I'm definitely not against that, but I think we can still improve on them, even though it's not simple.
Great, thank you. Yeah, so in connection with that, because it was very interesting, the comparison you made of the composite SCD for Eagle and then for COLIBRE, and then you see that it was doing quite a good fit, but the ultraviolet was not behaving so well in Eagle, but then it was actually doing so much better. So in your view, what is the reason? It's simply better resolution, or that these models are actually more realistic for this birth cloud dust attenuation?
Yeah, it's also that the spatial resolution in COLIBRE is better, but also it has this cold ISM physics where you naturally get more condensed cold gas around star forming regions, so which should be the case. But in simulations like Eagle or TNG, this was not the case because you did not have cooling down to the molecular regime. And so the resolutions are improving, and not just COLIBRE, some other resolutions with the multi-phase ISM are getting better in getting the structure of the multi-phase ISM right. And I think this makes quite a big of difference.
Okay, thank you. Any other questions for our speaker? It's too bad that when we put this in YouTube, people will not be able to ask questions. So I think this is a much better.
They can always contact me if they want.
Of course. And just one minor thing, just before we go, because I was a bit curious. You were saying that you had different methods and you had this tetrahedral guide. So when you were doing the gridding, the grids, and you were saying it was not so successful. So could you just comment a bit on that briefly? Why this did not work so well?
Because actually, we thought the reason why we tried that is because tetrahedra, of course, are relatively simple, and shooting photons through them is relatively simple because with the Voronoi grids, you always have to test which wall you're gonna go next to. For the tetrahedron, that is actually there's algorithms that make that very efficient. The main disadvantage is in 3D, you need a lot of tetrahedra. So you still need a lot of grid cells to have the same effective resolution as a Voronoi grid. So the
Okay.
fact that that shooting photons through a single tetrahedron is more efficient doesn't weigh up against the fact that you need way more tetrahedra to get the same effective resolution as for a Voronoi grid.
Okay, I see.
But it was a fun master thesis project, and
I can imagine.
yeah, so the student liked it a lot, and it was worth trying.
Absolutely. Okay, so I guess time has run out, but thanks so much, Maarten. It has been a really, really nice talk, very pedagogical. I think this would be a nice reference for people, for students who want to learn about the effect of dust. I think that the introduction was really, really good. So thank you very much. And well, thanks everybody for attending this talk. So take care.
Thank you. It was a pleasure to be asked.
Thank you. Take care. Bye-bye.
Bye.